In the name of God, hello dear students of grade 11. Welcome back to Thinkable Physics YouTube channel. My name is Masood. So far we talked about a capacitor and we said that capacitor has a function and the function of capacitor is storing energy in the form of charge. And we concentrated especially on one type of capacitor, which is parallel plate capacitor. Parallel plate capacitor consists of two metal plates and a dielectric. Dielectric, I mean insulator. Maybe this dielectric might be glass, air, paper, any dielectric, right? So this dielectric is sandwiched between two metal plates, right? And right now we are going to complete our study about especially we are going to actually focusing on what? We are focusing in this lecture on the role of the dielectric in capacitor. Let's get started. The title of our subject is material between a capacitor's plates can change its capacity. So material between the plates can actually affect the capacitance of the capacitor. Inserting a dielectric between the plates of capacitor results in what? So embedding or inserting or putting a dielectric, putting an insulator between two metal plates of a capacitor has an effect, right? Has some actually influences. What are these influences? Let's read them one by one and I'll break it down for you on this figure. Number one, putting a dielectric reduces the electric field. Reduces the electric field of the capacitor, right? Firstly. Number two, increases the charge. They are the effects of putting the dielectric in the capacitor. Reduces the electric field, increasing the charge, increasing the capacitance. So having dielectric or existing dielectric between two metal parallel plates results in reducing electric field, but increasing charge and increasing actually capacitance. I'm going to break it down for you. I want you to be with me to better understand the subject, right? So this plate and this plate, they are actually they are plates. They are parallel plates of the capacitor. This is positive terminal. This is negative terminal of the capacitor. The direction of the main field is from positive to negative. Direction of the field of the capacitor is started from what? From positive terminal to the negative terminal. This is main electric field. But if you take a look at the direction of the dielectric, actually direction of the dielectric, direction of the electric field of the dielectric is the what? Is opposite, like this. Over there, actually, it's electric field is always started from positive terminal to the negative terminal, positive charge to negative charge. If you take a look at these fields, they are opposite. That's why whenever you want to find the net field, you have to subtract what? You have to subtract the field of the dielectric from the main field. So I can say field of the dielectric, main field minus what? Minus field of the dielectric. That's why main field of the capacitor reduces, right? Main field reduces. Why this phenomenon is taking place? Let me explain it for you. When a dielectric actually is embedded between the two plates of a capacitor, particles of the dielectric realign themselves. They realign themselves. Actually, near the positive terminal, electrons are arranged. Near the positive terminal, electrons are dielectric, and near the negative terminal of the capacitor, protons or positive charges are arranged. They are realigned. So this array of atoms, this array provides what? Provides a electric field, which is opposite to the electric field of the, which is opposite to the main field. That's why whenever you want to find the net electric field, you have to subtract this one, because the direction is downward. For example, in this figure, downward, the direction of the main field is upward. So it's clear that the main field of the device is reduces. This is the first effect. The second effect is it increases the charge. How does it increase the charge? Let me jog your memory about the equation of the electric field. Electric field is equal to what? F over what? F over Q. Electric field. We have this rule in chapter 6. We got it in chapter 6. Electric field is found by this equation, F over Q. So right now I want you to find the relation between electric field and charge, right? You know that the electric field here in this equation is reciprocal to the charge. They are inversely proportional to one another. That's why the less the electric field, the more the charge. That's why whenever you say electric field reduces, this reduction results in what? This reduction in electric field results in increasing the charge, right? That's the second factor. The third one increases the capacitance. How does it increase the capacitance? I wanted to think about the equation of capacitance, the main equation of capacitance. Let me write it here. I'm not going to erase these equations, right? This one about the first, this equation actually refers to the first factor. This equation refers to the second factor. The third factor, I'm not going to erase them. I want to write it here about the C, about the equation of C. C is found by this by which equation? I wanted to go over it, right? Which equation? General form of the capacitance. C is equal to Q over delta V, right? Q over delta V. So could you tell me which relationship is there between C and Q, right? We said that charge increases, and in this equation, in this factor, it's a factor number 3, increases the capacitance. How does it increase the capacitance? Because charge increases, so capacitance increases as well. So I can say capacitance is directly proportional to the Q. And by the way, this Q, the symbol, if you actually use lowercase or capital letter, it doesn't matter. Q small or Q capital, it's the same. We mean charge. Q means charge. Whether you write it in a small letter or capital letter, it doesn't matter. So I can say putting or inserting the dielectric results in 3 things. What are the factors? The first one, reducing the electric field. This reducing the electric field results in what? Results in the increasing the charge. And when the charge increases, automatically capacitance increases, because capacitance according to this equation is directly proportional to the Q. Right. Let me erase these equations. So we have the equation. We have the I told you in advance about this equation. It says according to the equation E is equal to F over Q. E is inversely proportional to the Q. It means E, as it decreases, Q increases. I explained it for you. The second explanation, according to C is equal to Q over delta V, C is directly proportional to the Q. It means Q increases. As Q increases, C increases as well. Dielectric actually might be air, rubber, glass, anything. So you know that the dielectric is insulator, right? This is about the. I want you to answer this question. This question, I'm not gonna answer them. I want you to answer this question and actually comment the answers for me to make sure you understand the subject. Question number 1, it's a capacitor with no material between its plates. When there's no material between two parallel plates, what's the name of the actually capacitor? Vacuum capacitor, A. B, dielectric capacitor. C, spherical capacitor. D, A plus B. So just circle it for me and comment the answer for me before I send the PDF for you. PDF of the answers. Question number 2. It's a capacitor with an insulator between its plates. Insulator, it means number 1, vacuum capacitor. A. B, dielectric capacitor. C, spherical capacitor. D, A plus B. Right. Question number 3. Choose the common dielectric or dielectric in capacitors. Just choose them. Which one? Just circle one option. Number 4. It's an insulating material inserted between the plates of a capacitor. So this is the definition of what? Right? It's a definition. It's an insulating between the plates of a capacitor. Just write the title. Right? Question number 5. Dielectric between plates of capacitor. Space. We have a gap here. How do you fill the gap? A. It says dielectric between the plates of a capacitor. A reduces E of the capacitor. B increases the C. C increases the Q, or all of the above. And I want you to go over it. If you understood the subject, you can circle them. Question number 6. The goal to use dielectric is to increase or decrease the capacitance of the capacitor. So what's our objective? What's our aim actually? To use the dielectric inside the capacitor. Do we want to increase the capacitance or decrease the capacitance? Just go over it and answer. Number 7, how is a capacitor energized? And I told you, energized means charged. Charge of any device, charge of cell phone, charge of battery, charge of capacitor is similar. You have the same actually procedure. How is the capacitor energized? I answered them for you, and I'm sure you know the answer. Actually connecting the two terminals of the battery to the two plates of the capacitor. Plug in the actually two terminals of the capacitor to the two terminals of the battery by connecting the plates of the capacitor. I explained it for you in advance, right? Number 8, during charging of a capacitance, charge transfer stops when? So you have to circle the condition of actually, or in which situation actually charge transfer stops, right? In which situation? Read them and answer them. After that, question number 9, open circuit we have a gap. Open circuit is space. Electricity conducts electricity or does not conduct electricity. Open circuit means there's an interruption. Open means there's an interruption, and I drew it for you in previous lesson. We said that open circuit means there's a cut. There's a cut in the circuit. For example, this is the wire, and this is the wire. Right now, in this situation, this is an open circuit. So the circuit is not connected. Right? Does this circuit, open circuit, conduct electricity or not? I want you to circle one of them. Closed circuit, space, electricity. So closed circuit means there's no cut in the wire, there's no cut in the circuit. Like this one is open, and this one is closed circuit. Closed. This is the one terminal of the wire, and this is another terminal of the wire, and there's no interruption, there's no cut, right? So the circuit is one. The circuit, I can say, is on. So does the circuit actually conduct electricity or not? Tip number one: when the switch is on, the electric circuit is called closed circuit. When the switch, so this actually figure represents a switch, like the switch of the bulb, for example, right? So when the switch is on, so I want you to guess the answer. In which situation the switch is on? This one or this one? In open circuit, we have the switch is on, or in closed circuit, right? And I told you in open means there's a cut in the circuit. When the switch is on, the electric circuit is called closed circuit, right? Tip number two: when the switch is off. What's the switch is off? Think about it. I'm not gonna spoil it. I leave it for you. I leave the answer for you. Just take a look at these figures: open circuit and closed circuit. So when the switch is off, I'm not sure. For example, I'm not going to reveal. I'm not sure whether this one is, in this case, switch is on, or in this case. I'm not sure whether in this case switch is off or in this case, right? I want you to go over it and comment the answer for me. When the switch is off, electric circuit is called open circuit, right? Open circuit, closed circuit. In which situation switch is on, in which situation switch is off, in which situation electricity conducts, in which situation electricity does not conduct, right? Think about it. And this is this figure. We have two figures. Open circuit, you see the switch is off here. The switch, this open circuit. In this case, we have closed circuit. The switch is on, right? I want to leave this subject for the next lecture. I appreciate you for being with me, and bye-bye.